All right, so this week we're going to be looking at sequences. This work that we're going to do in this section is not all directly supporting what we're doing in section 5.5, but that is the section that this is sort of meant to help. The idea here is really working on our pattern recognition skills. In section, I believe it's 5.5 in the parent class, we're looking at the Fibonacci sequence. And the Fibonacci sequence is a sequence of numbers with a specific pattern to it. So what I wanted to do here is kind of practice looking for patterns in sequences of numbers. First thing I want to do is just give a loose definition of what a sequence is. There's a very formal definition that we don't need to talk about here. We just kind of want the intuitive one. So when we talk about a sequence, what we're talking about is an infinite list of numbers. They're usually separated by commas, and you list them out one by one. And there's no requirement in the definition of a sequence that any pattern exists. The numbers can be completely random, and it would still be considered a sequence. But the kinds of sequences that we're interested in are the ones that do have a pattern. And our goal here is to become proficient at finding that pattern and then using it to continue the sequence on our own. So there's three specific types of sequences I want to talk about. Two of them you should have encountered already toward the end of intermediate algebra. And those are arithmetic sequences and geometric sequences. Now, in an intermediate algebra class, you do a lot more with these than we're going to do here. You come up with formulas that you can use to immediately find any number in the sequence that you want, or that allows you to sum the first n terms of the sequence, add them up, using a nice closed form formula. We're not doing any of that stuff here. Our goal is simply to learn how to recognize the kinds of patterns that appear in these sequences and then use them to keep finding more terms in that sequence. So really quickly, to review what those are, an arithmetic sequence is a sequence where each term after the first term is equal to some number d, which we call a common difference, plus the previous term. So basically in an arithmetic sequence, the first term is kind of arbitrary, it's whatever it is, and then to find each new term in the sequence, we have a specific number that we keep adding to the previous term to generate that sequence, and we'll look at some examples of that. A geometric sequence is defined in a very similar way, except instead of adding a number to each previous term in the sequence, we're multiplying a number to each previous term in that sequence. And we call that number that's being multiplied each time the common ratio. Okay, so we'll look at examples of those as well. This next term is not an official one, that's just one I'm using. I'm calling these sequences Fibonacci-like sequences. Again, at the end of chapter 5 in our parent class, we talk about the Fibonacci sequence, and it's defined in a very specific way, but there's lots of other very similar sequences that can have the same general idea, and I'm going to call those Fibonacci-like sequences. The way we define those here is they are sequences where the first two terms are kind of chosen arbitrarily, and then every term after the second is equal to the sum of the two previous terms. You grab the two terms that come right before whichever term you're looking at, add them together, that should give you the next term of the sequence. So we're going to work through 6 examples here, and I'm going to verbally identify whether they're arithmetic, geometric, or Fibonacci-like, and then I'm going to work out the next 2 terms in each sequence once we've determined that. So let's start with this one. 3, 8, 13, 18, and then I need the next 2. So in this sequence, this one turns out to be arithmetic. And the way that I determine that is if I suspect that it might be arithmetic, I take consecutive terms, one right after the other, and I subtract the second term minus the first term, or the later term minus the earlier term. So 8 minus 3 is 5. What that means is that to get from 3 to 8, I could have added 5. That might be how I got that 8. Then if I do that for the next pair of consecutive terms, 8 and 13, and subtract 13 minus 8 is also 5, which means to get from 8 to 13, I would have taken that 8 and added a 5. And notice 18 minus 13 is also 5. So it appears that in this sequence, to get from one term to the next, I'm adding 5 each time. That 5 right there is that common difference that we're talking about up here. That D that appears in the definition of our arithmetic sequence. Notice it has to be the same number that's being added each time. I can't be adding different numbers each time because then that pattern breaks down. So if I'd like to continue this pattern, now that I've recognized it as an arithmetic sequence, I need to continue adding 5 to each term. So starting at this 18 here, 18 plus 5 is 23, and 23 plus 5 is 28. Those would be the next two terms in that sequence. Okay? This next sequence here, 4, 1, -2, -5. If you compare it to the previous sequence, you'll notice right away a comparison between the two, or contrast them, I should say. In this sequence, the terms are getting larger as you progress through the sequence, whereas in this one, they're getting smaller. But despite the fact that one is getting larger while the other one is getting smaller, they are actually both arithmetic sequences. So using that same idea, if I take the first pair of consecutive terms and do the second one minus the first one, 1 minus 4 is equal to -3. And if I continue that, -2 minus 1 is also -3, and -5 minus -2 is also -3. So what's happening, you can think of it as subtracting 3 each step of the way, or if you want to keep it in the same, vein as other arithmetic sequences, you can also think of this as adding -3 each time. Notice there's nothing in the definition of arithmetic sequences that says you have to be using a positive number as your common difference. It could be negative, in which case the terms will be getting smaller. So I'm adding -3, or again, I can think of that as subtracting 3 from each term in this sequence. To get the next one, I would do -5 minus 3, which is -8, and then -8 minus 3, which is -11. Those would be the next two terms in that sequence. Okay? Now, moving on to number 3. If we approach this one the same way as the previous two sequences, we're going to run into a problem. So if I take the first two terms and I subtract them, then I have 12 minus 6, which is 6. So if I was going to continue like I did with these arithmetic sequences, I would write a plus 6 right here, getting from 6 to 12. But then if I subtract the next two consecutive terms, 24 minus 12, I don't get 6. I get 12. So that's plus 12. And then same thing here. 48 minus 24 is 24. I would have plus 24. The number that's being added each time is changing. So it's not common. It's not a common difference, which means this is not an arithmetic sequence. However, I'm noticing that the gaps between these terms is getting larger each step of the way. And something that might be causing that is multiplication instead of addition. So let's think of this in a different way. If I want to figure out what I need to multiply to the number 6 to get to 12, what I could do is reverse that and use division. So if I take the second term divided by the first term, 12 divided by 6, that's 2. Or in other words, I'm multiplying by 2 to get from 6 to 12. If I do that here, 24 divided by 12, that is also 2. So it looks like I'm multiplying by 2 to get from 12 to 24. And then the same thing checks out right here. So instead of adding something to get each new term in the sequence, I'm doubling it. I'm multiplying by 2. So that means that the pattern should continue if I keep going this route. So this is a geometric sequence. 2 is the common ratio this time. And to get the next term in the sequence, I'd have to multiply 48 times 2. That's 96. Okay? And then I would do the same thing here. I would double this, and I would get 192. Okay? So that's a geometric sequence. Now let's take a look at this guy. This one's interesting, kind of like this example over here, number 2. The sequence is decreasing. Instead of getting larger with each new term like we did here, it's getting smaller with each new term. But if I tried using my approach that I did in the first two examples of looking for some common thing that I'm adding each time, you're going to find that it's not the same number. 18 plus -12 would give me 6, but then 6 plus -4 is what gives me 2. So it's not a common difference. This turns out to also be a geometric sequence. And you may look at that and think that doesn't really make sense, because I think that when I multiply a number by another number, the result is supposed to be bigger. And that's actually not necessarily true if the number that you're multiplying by is a fraction that's less than 1. So in this case, if I do the division like we did here, 6 divided by 18 is 1/3, which in other words means I'm actually multiplying by 1/3 to get that 6. 18 times 1/3, which you can verify. Remember, multiplying by 1/3 is the same thing as saying 1/3 of. So 1/3 of 18 is 6. I notice that if I also multiply by 1/3 here, 6 times 1/3 is 2. 2 times 1/3 is 2/3. And so I would continue that pattern. 2/3 times 1/3 would be 2/9. 2/9 times 1/3 would be 2/27. And so they continually get smaller and smaller because I'm multiplying by that fraction, 1/3. Okay? So these first two sequences were arithmetic. I'm just going to write that, arithmetic. These two sequences, number 3 and number 4, were both geometric. These last two sequences are neither, which, given the breakdown that we gave up here, would seem to imply that they're Fibonacci-like. And that's what they are. So in a Fibonacci-like sequence, what we're doing is instead of adding some common difference each time or multiplying by some common ratio each time, we're starting with two terms that are basically arbitrary. They can be any two numbers. And then starting with the third term, we obtain it by adding the previous two. Notice that 6 is equal to 4 plus 2. 10 is equal to the sum of the previous two terms here. 6 plus 4 equals 10. That's how we get these Fibonacci-like sequences. You recognize a Fibonacci-like sequence, at least in the assignment that we're going to be doing, if you've ruled out that it's arithmetic or geometric. Now, that's not true in general. There's all sorts of different kinds of sequences out there. Not just these three, but the assignment you're going to be doing this week will only have these three types. So if you've ruled out the first two types, then that must mean it's Fibonacci-like for our assignment. Okay, so the next term must be the sum of the previous two. 10 plus 6, that's 16. And then 16 plus 10 would be 26. That would be the next two terms in that sequence. Okay, this one is also Fibonacci-like, so I'm going to write that. Okay, so following that pattern, notice 0 plus 5 gives me this 5. And then 10 is equal to the sum of its previous two terms as well. 5 plus 5 is 10. So I can use that to finish out this sequence. 10 plus 5 is 15. 10 plus 15 would give me the next, which is 25. Okay? So hopefully that gets you a little bit of practice with recognizing patterns and sequences. And I think that general skill is helpful in a lot of areas, but should be helpful with the end of Chapter 5 in our parent class. So that's going to wrap things up for today.